Welcome to the fifth presentation in the series where we're looking at education as it moves into the future. We're seeking to gather the evidence about various aspects of the educational process, the evidence from research, and what does it tell us to guide us as we move forward. In this presentation, we're going to look at how we can handle basic statistics. Research in education generates numbers very frequently. How do we interpret them? Now, this is not going to be an overall coverage of statistical techniques. It's going to look at just one or two of the basic principles with reference to three techniques that are probably the most common ones that we might find useful. It's only just a beginning introduction of the principles. Let's remind ourselves that that's how we've described research. Systematic, coherent investigation. Some aspect of the world around, in our case, to do with learning and teaching, in order to find out what is happening, but even more important, why it happens that way. And this kind of research often generates numerical data, not always, but very frequently. Now, statistics is simply a way to help us to find the meaning of the numbers that are generated. Let's start by looking at what's known as the normal distribution curve. That's what you get to make any measurement with a large number of people, hundreds or thousands. Most people are somewhere about the average, and there are fewer at the extremes of low and high. A normal distribution because it always happens. Any measurement that can be randomly set up. Height, weight, test marks, exam marks, and the average in statistics is known as the mean. When this curve stops curving in and starts to turn round and starts curving out again, that defines a position which gives us the standard deviation, the gap between that point and the mean. And if you know the mean and the standard deviation, you know everything you need to know about the whole curve. 2 standard deviations above, 3 above, 4 above, we could go on. But there are very few candidates at 4 above. But it goes both ways. You can have a standard deviation below the mean, 2 below the mean, 3 below the mean, 4 below the mean. But these are very important. If you look at all the people who come in the area between 2 standard deviations below the mean and 2 above the mean, you will find always that that's 95% of all the students. Doesn't matter whether we measure their shoe size, their weight, their height, their marks in a history exam. If you've got a big enough number, it will always turn up to be that. If you go out 3 standard deviations out each way, it jumps to 99%. Just remember these figures, 95, 99, and if you go 4 out, it's 99.9%. In other words, people getting beyond that, extremely good, extremely poor, extremely tall, extremely short, is a very tiny proportion of the population, 0.1% of the population. And any normal distribution curve, any measurement like that will always give you these results if the sample's big enough. Now, when you put that together, (95% between 2 standard deviations above and below, that means there's 5% left at the ends called tails. That's the origin of our probability less than 0.05, significance at 5%, both saying the same thing. 3 standard deviations out gives you 99%. That gives you the probability less than 0.01, or significance at 1%. And then 4 standard deviations out, probability at 0.001, significance at 0.1%. That's the origin of these strange figures that you will see in all sorts of documents handling statistical information. All comes from this normal distribution. Now let's look at spreadsheets. They're incredibly useful. Now they were only invented in 1979. Software package called VisiCalc that was made available for the Apple Mac computer, which was the only basic big scale computer of the day. A wonderful invention. And it's just like a table, a grid. You can put anything in it. In this case, we put in 10 candidates, and you've got an exam paper with 5 questions, 1, 2, 3, 4, 5 across the top. And we put in the marks. Now it's entirely fictitious, but the spreadsheet can save you a lot of time because that's the only typing you really have to do. Because once you put the formula in, it does all the work for you. Now it doesn't make a big difference if you've got 10 candidates, but if you've got 1,000 candidates, it makes a huge difference to your workload. Now if you're in that box there, that box will be labeled G3. You can see the letters along the top, the numbers down the sides. So every box can be identified. And you put an equal sign in. An equal sign tells the computer, do the following calculation. Sum, add up, from box B3 to box F3, number 13 to number 17. Does it for you. But when it does it, there's a little handle on the box which you can pull down, and when you pull it down, it does all the other calculations for you. No mistakes, no errors, instantaneously. It saves a lot of time, and that gives you the total marks as percentages for all the candidates. Now you can do the same at the bottom left hand side for the mean and the standard deviation. Remember, the mean is just the average, the standard deviation is the measure of the spread. So in the first box there, for the mean, you type B3 equals average B3 to B12. You tell the computer, sum up between box B3 and B12 and take an average. And that gives you the figure 11. And in the box line below, the standard deviation, the same range. And again, the handles in the box, just pull them to the right and you get it for all the questions, including the total mark. So if you look at the bottom right hand corner, the average mark in this exam was 64% and the standard deviation was 8.7. Now remember, 8.7, if you double that, that'd be 17.4. Then if you go above the average by 17.4 and below by 17.4, 95% of all the candidates scored between these ranges. Wonderfully powerful and useful technique. Now, statistical packages are based on a spreadsheet idea. Now here's a picture of a very old version of SPSS. If you look at down at the left hand side, you've got variable and a whole string of things 1 and variable a whole string of things 2. It puts them to do it 2 decimal places, which is a bit confusing, but does that automatically. But let's suppose these were just marks, scores, choices, or something like that. Go down to Analyze, pull down that, pick descriptives, and then we're going to look for frequencies. It tells you how often a given score was chosen. But we're going to do it for variable 2. So that's the box that comes back. Click to variable 2 to move across, which it does, and you get that. Variable 2, these are the answers to a question in a questionnaire, where you had 1, let's say, strongly agree, and 5 strongly disagree, or vice versa. And it tells you that 3 people chose the strongly agree, 5 they agree, 6 were neutral, and so on. And it tells you the percentages. Now when you come to use it, that's probably the column, but round it to the nearest whole number. It always gives it with too many decimal places for good reasons, but for our purposes we can round it down, and I'll give some guidelines for that at the end. Now let's go back to original data. That was the second column, which was just responses to one item in a questionnaire. The first column is some sort of score or mark. Go back to Analyze. This time pick Descriptives. Now we're going to bring across variable 1, which I've already done for you, so that's in the right hand box at the top. So we're asking for the descriptors for variable 1, and that's what it comes up with. Again, it's a sea of numbers, and I'll show you how to simplify that. Variable 1, the sample was 20. The minimum mark was 1, the maximum was 20, and the mean was 8.25. Standard deviation 5.4. Now, you would simplify that, so if you're writing this up in a thesis or a presentation, you'd simplify that to look something like that, and colour helps the reader to spot the various things. Notice I've rounded the mean to 1 decimal place, standard deviation to 1 decimal place, which is reasonable. Right, that is just using statistics to give us a summary of what our measurements are saying. Now let's move on to the broad groups of statistics. We've got parametric statistics, and you might imagine the non-parametric statistics. You've got to use the right one. You've got to know which is which. Parametric is when your data is integer, like shoe sizes, weight, height, marks. Where if you've got 50, it means it's twice 25. So you've got possible things for us are test scores and examination marks. That's the most likely ones. Non-parametric is for ordinal data. That's just first, second, third, fourth. Now that's questionnaire data. They pick the first box, second box, third box, fourth box. You can't say the value of the second box is twice the fourth. You may number them 5, 4, 3, 2, 1, but the numbers are just putting it in order. You could have used alphabet letters. On a computer program can't handle alphabet letters. It must have numbers. So data from questionnaires is always non-parametric, and you must use the right statistics, and that's a major source of error. Statistics that require integer data are these ones. That's because the mathematics behind them makes assumptions which assumes that the data are integer. They're real numbers. Kendall's tau-B correlation and chi-square, they don't make that assumption the way the formula have been derived. So they are useful with ordinal data. But you must use the right ones. Now, how big has your sample got to be? The problem is people vary, so you can't make deductions by taking a sample of 1 or a sample of 10 or even 20. But how many have you got to take? We need a large number, and it depends on the statistics how large it's going to be. But here is a kind of rule of thumb. Don't take it too accurately because it varies from statistic to statistic, but it gives you a broad brush picture. Normally, if you've got a group size of 200, most statistics work excellently. Now, if you're comparing boys and girls, then that may mean 200 of each. Although you can get good results from a bit less. You can still get quite good results in that range. Again, it depends on the statistic. Even that can be useful, but you've got to be cautious. That one, well, it depends on the statistic. Probably if you've got less than 20, statistics is not the right way to go. But that's just a rule of thumb. It's a broad brush picture. We don't take that too precisely. It's just a guide. Now we're going to look at 3 broad techniques. That's the only 3 I'm going to look at, and they're probably the ones that are the most common ones that we need in educational research. But there are many other useful ones, but just picking up 3 to illustrate a few points. The computer does the work, but we've got to know what to put in and how to interpret what comes out. We're going to look at correlation, then t-tests and related tests, and then chi-square. Let's just take these in turn. Correlation. Now the question you're asking here is, if you've got 2 examinations, for example, in 2 different subjects, to what extent are those with high scores in the first subject the same as those with high scores in the second subject? Or it could be the marks in one subject at 2 different points in time. So that's what correlation is actually doing. And it doesn't matter how you do it, it comes up with a correlation coefficient, which always has the symbol r, small r. And the value of r can range from -1 to +1. Now, let's look at +1 first. If it's +1, it means that those with the top score in the first exam are the same as those the top in the second. Those who came second in the first, second in the second, and so on down through the line right down. It's a perfect match. If it's -1, it's reversed. Those with the highest mark in the first exam got the lowest mark in the second. Highly unlikely. If it's 0, then there's no connection between the orders at all. Now, there are some problems with correlation, but they're easily resolved. There are 3 ways of doing it, and they're named after 3 famous statisticians of the earlier part of the 20th century: Pearson, Spearman, and Kendall, who did wonderful work in giving us our statistical insights that we take for granted today. They're all determined by what the data's like. If your data is integer data and normally distributed or approximately normally distributed, Pearson's the right one to use. So exam marks with a big enough sample where you get a normal distribution, that's what you do. Spearman calculated quite differently. Integer data, but the distribution isn't normal. So if you've got a smaller sample or there's something unusual about the way the distribution is, that is very, very useful. Kendall, he produced a method where the data are ordinal. In other words, they're like first, second, third, fourth. They merely put people into groups in order, but the numbers don't have any meaning beyond that. And there's no distribution requirement at all. It could be anything. All 3 are incredibly useful, but you must use the right one. Let's look at just something very simple and trivial. You've got 2 variables here, and I've just put in some scores just with 5 candidates to illustrate this. Test 1, Test 2, 5 candidates sat both. Or it could be 2 questions in one examination. You go into Analyze, select Correlate, go for Bivariate, which just means 2 variables, bivariate, and it comes up with that, without the coloured arrows. Now you've got to select the variables with the red arrow, but you've also got to decisions further down. So you first of all, you bring your variables across, you select which method you want to use, and if you're not sure you can use 2 or more. Assume it'll be 2-tailed unless you've got evidence otherwise. 1-tailed is when the correlation can only be one way, therefore only one tail of the curve can apply. It doesn't alter the calculation, it alters the probability. So let's just look at that. We've got integer data normally distributed, so Pearson is correct. 2-tailed, because we've no reason to believe it has to be one way or the other. So that one's okay. That one's okay. Now, the 2-tailed, 1-tailed, you probably won't use that much, but you have to get Pearson or Kendall's Tawby or Spearman correct. And if the data are of 2 different types, then you can pick 2 of them and compare the results. You can see the differences. Now, a word of warning. Interpreting it, the biggest problem in statistics. Correlation always shows association. It doesn't indicate causation. In other words, getting a high mark in test 1 isn't the cause of getting a high mark in test 2. Correlation doesn't tell you that. It might be, it might not be. It can't tell you that. It merely tells you that there's a tendency for those who do well in one to do well in the other, if it's a positive correlation. Now the value of the coefficient shows you the strength of the association. It's a perfect association if you get a value of 1, and a perfect reverse association if you get a value of -1. No association if you get 0. So the size of the value tells you the strength of association. Computer will tell you the probability that that happened by chance, and it comes back to looking at it at 5%, 1%, 0.1% from the normal distribution curve. And the probability value is controlled by the sample size. So if you've got a very big sample size, then the chance of a strong association happening by chance is very, very low. Now let's move to the next one, the t-test. Now t must be lowercase t. It's worthwhile searching and looking at the origins of that test and its peculiar history. Brilliant piece of work. Now what that test is answering is, if you've got data for 2 samples who've sat the same test, same measurement, and you're asking, are the differences that you see, are these differences statistically significant, or could they just have happened by chance? Now t-test has got several options. If you know what the population is going to be, you can see your sample is the same as the population. You're not going to meet that one quite so often, so I'm fading it down a bit. Looking at 2 samples that have no connection with each other, 2 classes, 2 groups, a population has been taught one way, a population taught a different way, boys, girls. All of that is unrelated samples. That's a common one. If you pair them up, so you've got a test done with the same students on 2 different occasions, and you're looking to see whether there's an improvement or not, use that one. Again, I'm going to fade that one down. It's less likely. If it's 3 or more samples, then you've got an extension to the t-test and you're into the area of analysis of variance. I'm going to leave that for the moment. Principles are the same. So I'm going to focus on this one, which is probably the most common one that you will use. Again, let's look at something completely trivial. Variable 1 and 2, and I've just thrown in some figures there. Are the performances different or the same? Now there is your options offered. And we're going for the independent sample t-test. That just compares the performance of 2 unrelated samples. And that's the one that's probably the most common one. Now, let's look at one that's more real life. Again, it's fictional data. The variable 1 on the left is the score. So they've sat a test and they've got a score that looks like it's out of 20. But some are boys and some are girls. So that's been coded in 1 or 2 because the computer can only handle numbers. But these numbers have no meaning. You can't say a girl is worth twice a boy, or a boy is worth twice a girl. Let's look at that now. We're going to compare the means of these 2 samples, the boys and the girls, with the independent sample t-test. They've all sat the same test. So that's what, when you go in and look at correlate, pick independent sample t-test, that's what it offers you. So score, that's the one you're going to have to take across. We'll take gender across just in a moment. You've got to take one or other, but the score goes across and gender's left. Because the gender is what we call the grouping variable. That defines the 2 groups, boys and girls. Take that one across, but you get 2 question marks. So you've got to click the button underneath it which says define groups. The computer's got to be told what's the label you've given to the gender. You've called group 1, let's say it's boys, 1, and group 2, girls. And it's a 2. You come back to the original sheet and it shows it now as gender 1 and 2. The 1 and the 2 define the gender. The marks themselves define the score. So you now just press OK and it will do the computation for you. And you don't need to worry about it. If you do it wrong, you just go through it again. It does it so quickly. And it comes up with an output like that, and your eyeballs kind of glaze over when you look at all that sea of numbers to all these decimal places. It has to show it this way because it doesn't know what the user actually wants or the accuracy they require, and therefore it has to give all the possibilities. But for our purposes, we're only going to focus on a small range of things. Our gender, our sample sizes were 15 each, the means and the standard deviation, except we're going to round them down and reduce the number of places after the decimal point. And the actual findings, we're going to focus on these two numbers. The t-value, but we've assumed the variances are not equal. Variance is related to standard deviation, and if you look at the standard deviations, they're not equal. So you pick that one. In this case, it doesn't make any difference, but in some cases it might. And it gives you, for a two-tailed test, the probability is 0.009. Now that is less than 0.01, which is how it would be quoted. Now for most purposes, we don't need the rest of the data that's on that particular table. So that's what you end up with. And again, I've used colour, which just helps us to focus in. Let's say 1 was the men, 2 was the women. Sample in both cases 15. The means to 1 decimal place. Standard deviations, I put it into 2. The t-value, again to 1 decimal place, negative 2.8. And that's given as equal to 0.009, which is less than 0.01. Remember, we looked at 5%, 1%, 0.1%, the standard cutoff points by standard deviation. Now if you're going to put it in the text in a thesis or a paper, you'd write it like this. The conclusion: the women perform better than the men. T equals 2.8, probability less than 0.01. Now you don't need a negative sign now. The negative merely told you that group 2 was better than group 1. It would have been positive if group 1 had been better than group 2. But you've now defined that the women perform better, therefore the sign is no longer relevant. So that's the t-test, and all that ANOVA does is take it into more than 2 samples. Let's look at chi-square. Now the mathematics of this statistics is incredibly simple. You can do it almost in the back of a postage stamp. But to do it and employ it correctly is amazingly complex. And because of that complexity, it's not easy to see when a computer does it. Therefore I've written programs that do this, which makes it easier to follow. Advantage: it can handle ordinal data. It looks at distributions of choices as in a questionnaire and compares them. Are they the same or different? No distribution requirement required. Group sizes can be very different. Mathematically, it's very simple. But the problem comes because there are 2 ways of calculating. That's the first problem. And you've got to use the right one. Category size, there's a minute restriction on that. I'll show you an example in a moment which illustrates it. Then you've got a thing called degrees of freedom, which causes people to be confused. But you also need what I call a table of critical values, because you come up with a number and you've got to interpret the number. Let's look at these. Simple yet complex. That's the biggest problem. And it's not helped by literature. People have used different phrases to describe the 2 methods. And it causes a bit of confusion. Now this is the language I use, and I think it's much clearer. If there's a control group, if you're comparing some group with a control group, then it's goodness of fit. How well does your sample fit the control group? If there's no control group, it's a contingency test. The first one, for example, might be if you've got a sample who you've gathered their opinions from a questionnaire and they've been taught the normal way, that's the control group. If you've got another sample have been taught by a totally different way and you give them the same questionnaire and you're looking at how they've responded to it to see if it's different from the control group, that's the experimental group. With no control group, the most common one is boys compared to girls. You can't say either's a control, they're just different. And you've got to use the right one the right way. Now the restrictions in the minimum category size Now there is disagreement across the literature, but this is the one I stick to, that no category should drop below 10% or the number 10. That's quite strict. Anything does, you must group adjacent boxes. I'll illustrate that in a moment. Now I've got very sound mathematical reasons for choosing that, but you've got to interpret it flexibly. When I give an example, a lot of this will become clearer. Degrees of freedom. Now here's some fictitious data. Let's say you've got sample 1 and sample 2. That's the number of people that chose, let's say, from strongly agree to strongly disagree on some question. 56 chose strongly agree out of 185 in sample 1, for example. 51 out of 207 in sample 2. And the totals have been put round in the pinkish colour and the greeny blue colour. Now, a degree of freedom, that's the formal definition. It's the number of these white boxes that you must know to know everything. If you've got the figures that go around the edge, that's in the greeny blue and the pinkish colour. In practice, this is how you get it. You take the number of rows and reduce it by 1, and multiply the number of columns reduced by 1. So here we've got 2 rows, minus 1 is 1, 5 columns, minus 1 is 4. So it's 1 times 4, and that's got 4 degrees of freedom. Now let's do the same one there, and we've got a little problem. That box is below 10%, it's also below 10. Now the way to get rid of that box and satisfy the criteria is to group these two columns together. Now what you're saying here is that those who said disagree and those who said strongly disagree are being just grouped together, so it is reasonable to do. And you end up with a box looking like that. So the last white box is now empty, and you'll find that the one just in on the left from it has got the total of the two put together. Doesn't alter the totals at the edge, and that makes everything satisfy the conditions. Show you why in a moment. Now I'm going to look at it as a contingency test just for the moment. So I'm taking the same data, but I'm just saying now it's girls and boys. This time I've got girls in the top line. Now if you don't group the data, you end up, when the calculation's done by the computer, that chi-squared is 22.0, and there are 4 degrees of freedom because it's 5 columns, 2 rows, which is 4 times 1. And the probability is less than 0.001. However, that breaks the rules. You must group it some way. It could be grouped to the left or the right. I've chosen to group it to the right, which is probably more logically sensible. So you end up with a table like that, but notice the degrees of freedom now is dropped by 1 because it's 4 columns and 2 rows, which is 3 by 1. DF now is 3. But notice the chi-squared value is very different, and the probability is different. If you don't group, you'll get inflated values of chi-squared, and you think it's significant when it's not. And that is the table of values. That's the one I just keep handy for myself. I put colours on it because it helps my eyeball to be able to interpret it. It was 3 degrees of freedom. We got over 12, 12.3. And if you look at that, that's bigger than 11.35, but it's less than 16.27. So the probability then is less than 0.01. And you can get these kind of tables online, copy them out and use them that way to save you having to rake through books. But probably you're only going to need the very lowest numbers of degrees of freedom. The higher ones are rare in education. And in a thesis or a paper, you'd write it that way. Chi-squared equals 12.3, DF3, probability less than 0.01. That's how you might write it. So that's the 3 statistics that we've looked at, just to get the principles. Now the kind of common errors that I see frequently again and again and again. People use the wrong statistics with questionnaire data. You must use non-parametric statistics. Most papers I see, most conference presentations I see, get that wrong. That's a serious error. And you've got to understand degrees of freedom, and that means you've got to look at this program a few times and maybe get hold of a good book. And you've got to group the data with chi-square. And you've got to use the right method of calculation, and I suggest the programs I've written are easier to handle because there's 2 separate programs. People use Pearson when it should be Kendall's Tau B. That's very, very common. People say at the outset, well, that's my limiting condition, and therefore we don't use the power of statistics. Don't do that. SPS will quote it as in the probability column as 0.000. Now you must write that as probability is less than 0.001 because probability at 0.000 is certainty, and you're never certain. SPS has to write it that way for clarity, but that's what it means. And people quote numbers to far too many decimal places. Here's just a simple rule of thumb that I find helpful. Percentages make it whole numbers. It helps the reader. Means to 1 decimal place. Standard deviations to 1 or 2. Correlation coefficients possibly 2. Could be 1. T-test values 1 or 2. Chi-squared values 1 decimal place. Now the computer holds all the numbers. You don't have to worry about losing anything. But when you write it up, simplify it. It helps the reader. All the extra numbers signify almost nothing. Now we're taking a deep breath, try to bring this together. This has been a fairly fast race through the principles. The first thing is you've got to look at your data and decide what it is. Now, there are other kinds of data, but in education it tends to be one or other of these 2. And just simply ask the question, does a number 4 mean twice a 2, or a 40 twice a 20, or 100 twice a 50? Exam marks, test marks, measurements like that, yes, that's true. Or is a number 4 simply bigger than the number 2? Questionnaire data. You can't say a strongly agree is 5 times the value of a strongly disagree because you've coded it 5 and 1. That's got no meaning. It's just much more than. So that's where it fits. And you've got to use the right methods. Parametric, non-parametric. And that's a source of major errors that are common. That's where we start. Then we've got to say what kind of question we want our statistics to answer, and that determines what you do. Now there's a very deep statement. It's worth copying out and pondering. In this world nothing happens by chance, but chance rules everything that happens. It's a lovely play on the word chance. And in fact, if you look at the physical world, they are ruled by the laws of probability. But because of the size of the particles at that level, it doesn't happen by chance. I'll leave you to ponder that one. Probability and chance cause terrible problems. P less than 5% or less than 0.05 is simply saying I'm 95% sure that my findings did not arise by chance. And that one, I'm 99% sure that my findings did not arise by chance. Or I'm 99.9% sure that my findings did not arise by chance. That's the way to interpret these strange symbols and numbers. And different people use different symbolisms. I put in the 2 most common ones and how you would interpret that. So we've looked at three important statistical techniques. Correlation is always small r, t-test is always small t, and the chi-square is the Greek letter chi with a square in it, because in fact there's a square in the calculation. Correlations just ask the question, are two measurements associated? So that high in one means high in the other. But remember, there are three methods, and it's not causation. Now, it may be causation, but you have to have other evidence. So when it came to the work in memory studies and the great work of Johnston in a previous presentation, he didn't rely on correlation. He had other evidence that it was causation, and then the correlations obtained, we now can interpret it. And you must use the right method. The t-test, two sets of performance data different, or if it's extended into ANOVA, it can be more than two. And it must be integer data. And it must be approximately normally distributed. It can be quite skewed, and it'll still work. Two or more patterns of response is different. Typical questionnaire data. But remember, there are two methods depending whether there's a control group or there's no control group. And watch interpretation and grouping and degrees of freedom. Once you've done about 4 or 5 calculations, maybe up to 10, you find it just grows on you. It's easy then. You never make a mistake. But it takes a bit of practice to get the hang of that. So I've looked at these three simply because these three are probably the ones that are most common in the education area. There are other important ones, but time prevents us looking at them in this presentation. So statistics is to help us make sense of what we get from our studies and research. Chapter 16 of the book there, which you can download or buy, the chapter on its own, has got a chapter on statistics with a bit more detail. This one's online and you can just download it. And there's a section towards the end on statistics there. Don't worry about it coming from the physical science area and higher education. The principles are exactly the same. Still useful. And I've shown what it looks like, the book, in its second edition on screen. But there are many other books. Some of them are very accessible, and some of them I will just leave aside. Either they're too mathematical or they make too many assumptions in the presentation. We've done research on statistics and understanding it. It is a very difficult subject to understand, but there are ways round it. So take it all with great care and don't start panicking when you find it difficult. You've joined a group of many others who also find it difficult. But hopefully this presentation and the chapters in these books will take you a bit more along the road, but the best way to learn it is to do it. And if you make mistakes, don't worry. The computer doesn't judge you for that. You can do it again and again and just try things out. Yes, we've been pushing a boulder up a steep slope. Educational research is often that way. Now, the next presentation we're going to look at sharing our research results so that others, whether they're teachers or teacher trainers or educational planners, can be kept informed. So we're going to look at the world of publication and see where we go in that. So we're going to move on into that area in presentation 6.